we're going to take up a second way to find a rate law. And this is based on a notion that is called the integrated rate law. Okay, the integrated rate law is really going to be something we can use as a model. And then we say, if the reaction, for example, has first order kinetics, we can know some things about what the data for it should look like. We can then compare the data to that model and decide whether it really fits that description. Okay, so let's first develop the actual equations for the integrated rate laws, and then we'll look at how to apply them to determine the rate law for a reaction. Okay, so think about the rate law problem as being a little bit like a trajectory problem in physics. Okay, what do I mean by that? In a physics problem, if you know the initial position and you know the initial velocity vector for something, you can figure out where it is at any time later, right? By just doing the equations of motion. In a reaction, if I know the initial concentrations and if I knew the rate law essentially is the thing that tells me how fast the reaction is going, I should be able to predict what the concentrations would be at any time later, right? How much of my reactants had been used up, how much product had been made, things like that. So mathematically, what this is what's known as an initial value problem, which it has, in this case, a very simple looking differential equation in it. Now, this is one of the only classes, pieces of the semester where we actually will do a teensy bit of calculus in this video, okay? It's not central to what we're gonna do, and if you don't follow that, or there's very few of you, if any, that are not at least in Math 151 right now, and so nothing we're gonna do here should be surprising very many of you, but you're not actually going to have to do an integral, but the name integrated rate law comes from the fact that we get the integrated rate law by taking the rate law and integrating it. All right, so let's look at how this goes. We're going to develop what the integrated rate law would be for a zero order reaction, a first order reaction, and a second order reaction, because those three cases cover a lot of different chemical reactions. There are some others, that's not everything, but that's enough to keep us going along. Zero order is the simplest case. It's a fairly trivial one. An example of a zero order reaction would be the rate of, I don't know, evaporation of a liquid from a, say, cylindrical container. In that instance, the rate is zero order because only the molecules that are in the very top layer can evaporate, and every time one of those molecules evaporates, another molecule takes its place in the top layer. So the number of molecules sitting at the surface is essentially always the same. If we did this, the change in the concentration of the liquid, say, with respect to time, would just be constant, right? The evaporation rate says the liquid would just go down at a steady rate in that case. That says if I plotted how much liquid is still there versus time, the graph would be linear, right? The rate is the amount of liquid, say, versus time. And so if I plotted the amount of liquid up here, and time here, if it's going down linearly, that just says it'd go like that, right? So I really should have had a minus sign up there, I suppose, to make that make sense. And in that case, the slope of this, which is now it's a line, so the slope is constant, and that's just minus k. That's a case that doesn't happen very often. So if you're lost and you're guessing the order of reaction, probably don't guess zero, because most real reactions are not zero order kinetics. Let's take the first order case. So here I have molecule A just falls apart, makes two pieces of some sort, which I wrote as product P. Doesn't really matter what is over there. We're declaring that we believe that we're thinking about a reaction that is first order in the reactant, okay? So that says the rate is equal to minus the change in concentration of A over the change in time. And if it's first order, that's equal to the rate constant K times the concentration of A raised to the first power, okay? Now, so that's my rate law with deltas in it. If I want to look at how to develop the integrated rate law, and I'm just going to kind of step through this and then show you the equations that result. The first thing to do would be to change those deltas into differentials, right? So the delta is a change in something. When we do the delta, we're saying it's a finite change. But I could write this by saying minus and just make them differentials. Right, so I could do that. Then if I wanted to actually be able to integrate this, what I would do is I'd want to separate the variables. That's the fancy way of saying it. I want to put the terms with A in them on one side and the terms without A in them on the other. So I'm going to make this a deconcentration of A over A is equal to minus K dt, right? Then I would take that equation and I would integrate both sides of it. I would integrate it from, say, time equals 0 to time equals just some arbitrary time t. And then the concentration side would get integrated from the initial concentration to the final concentration, right? If I take this thing and imagine integrating it, on the left-hand side, we have the integral of d, concentration of A over A, which is just like dx over x. And so that's going to give us a log term, right? And on the right-hand side, I'm just going to get a minus k times t, and I evaluate those at the limits, right? So this one is going to get evaluated from the original concentration at time 0 to what we might just call concentration of A at time t. And this side's going to get integrated from, let's say, t equals 0 to just some arbitrary time t later. It's a little bit weird. We do these, we always write them this way, but it's kind of strange to write something where the variable and the limit on the integral are the same thing, but it will work itself out. So that says I'd get log of the concentration of A from the left side, I'd get minus KT from the right side, and I'd evaluate those at the limits, okay? If you do that, I'll just cut to what happens. The results for that, the integrated rate law really, there's two versions of it here, right? The top one says log of concentration of A at time t is equal to minus KT plus the log of the initial concentration, right? Where the 0 here means that at t equals 0. This one just means that whatever time t I put into the equation. Okay, so that one's in logarithm form. If I wanted to, I could do e to both sides of that. And if I did that, I would get the equation below, which says that the concentration of A plot would be, according to that, an exponential decay, right? So there's two ways we can compare this to something. We could say if I just plot, if I plot concentration versus time, that one starts at A0 and it comes down and it's an exponential decay. That's a really lousy looking exponential decay, okay? But it should be an exponential decay. The other way to do it is to take the log plot, and we usually talk about it this way because people like graphs that make straight lines, okay? And so here what I'm gonna graph is I'm gonna graph log of A versus T, okay? A is the reactant, so the concentration of A is going down. As the concentration of A goes down, the log of A goes down. This thing will be a line like that, and the slope of this line will be equal to minus K. How do I know that's true? The equation right next to it is the equation for that line, right? Because log of A, that's the y-axis, right? Over here, t is the x-axis, right? So if I just take that out, that's x. That makes minus k here be the slope. And then this is the intercept, right? So up here, if this is t equals 0, then that point there is the natural log of the initial concentration, okay? So what that tells me is that one way to tell if a reaction is first order is if I can measure the concentration of the reactant versus time, graph it as log of concentration versus time. If I get a straight line, that tells me my reaction is first order. And if I get a straight line, the slope of that straight line will tell me the value of the rate constant, okay? When I first learned about doing this stuff, we always said we wanted to make the plot that was a straight line because it's very easy to do that, and human eyes are quite good at looking at some data on a graph and deciding if they make a line or not. Nowadays, because there's lots of software to fit stuff, to be honest, we could also just plot this one. And if we plot this one, we'd have to use spreadsheet software or something to fit an exponential to it and see how good that was, right? If you just look at a graph, telling the difference between something that is an exponential and something that's curving with a slightly different shape, for most people, that's a harder task, right? So we usually describe this as trying to make what is going to be a linear graph. Can also do this for the second order case, okay? So if I have a reaction where reactant A reacts and according to second order kinetics, then the rate is still minus the change in A over the change in time. Now that's equal to K times A squared, right? Times concentration of A squared. This step here takes my separation of variables, right? And so that's the point at which I would change the deltas to differentials, right? So imagine writing this as D concentration of A, not D, I separated that out of there. This is A squared. right? And then again, I could integrate that from the initial concentration of A 0 to A at time t, and do the time integral from 0 to t, right? Now I've got the integral of dA over A squared, so that's going to give me a 1 over A when I integrate that one, right? And so the equation that I get if I do that integral and put in the limits from 0 to t gives me this equation, right? Rearrange that and we get the one down below. That one says if I plot 1 over the concentration of my reactant versus time, that should be a straight line, because now again, this is y, right? This piece is y. This is m times x, and this is b. This is, A is the reactant, so concentration of A is going down. That means 1 over A is going up. So this is a line like this, and the slope is equal to K. All right. So this gives me 3 models. The 0-order model says just plot concentration versus time and see if that's a line. The 1st-order model says plot log of concentration versus time and see if that's a line. My 2nd-order model says plot 1 over concentration and see if that one is a line, right? In general, not more than one of those will be a line, right? And so if it matches one of those models, then I'll figure out which graph is linear. When I do that, I will also get the rate constant K. Notice when you get the rate constant this way, you actually get the units for the rate constant from the units for the slope, right? So this is my 2nd-order rate constant, and its units what? On the y-axis, I've got 1 over concentration. So the slope is change in y over change in x. So on top, I have 1 over molarity. Underneath that, I have, let's say, seconds. So that gives me 1 over molarity and time. In this case, seconds, which are good units for a 2nd-order rate constant. Real quick, I'm going to flash back to the 1st-order case. Where is my result? Here we go. In this case, if I have this graph, to see that I get the units for the rate constant correctly here, I have to realize that before I take the log of the concentration, I have to do a little bit of manipulation to it. Specifically, I have to get it to be unitless, because you can't take the logarithm of molarity. So that log of A-axis actually has no units, and that means the slope here has units of just 1 over time. So if time's in seconds, let's say 1 over seconds, and those actually are the correct units for the rate constant for a 1st-order reaction, right? Because then I have rate is equal to just rate constant K times concentration. And in units, this is molarity over, let's say, seconds. This is molarity, so the rate constant needs to have units of 1 over seconds for that to work in that case, right? Again, the units for the rate constant will change if we change the order of reaction. And so you have to be careful of that and make sure you have them sorted out correctly. Right. This is a plot that I made by just declaring a rate constant, and I picked a rate constant of 0.693, which is a number some of you may recognize. I picked that because it made making one of those 2 graphs exceptionally easy, and we'll come back to that idea at the end of the video. But if you look at those, first of all, the red curve is the 1st-order reaction, so that one really is an exponential decay. The blue curve is 2nd order. That is not an exponential decay. It's actually dropping more slowly. I will submit that I think most people would have a hard time looking at, say, the blue curve by itself and deciding, is that an exponential decay or not, right? If you look at a lot of plots of functions, then you can probably do that. But ordinarily, it's not the sort of determination that we make easily, okay? What happens if we compare these 2 things? You'll notice that it takes longer to use up the initial amount of reactant in the 2nd-order case. The reason for that is when I come back, if I come back after a little bit of time, initially I set the concentration to 1 here just for simplicity, right? Suppose I come back after 1 second where I'm down here, right? My concentration is smaller now because in the 2nd-order rate law, the concentration is squared. That smaller concentration will have slowed down the rate more for the 2nd-order reaction than for the 1st-order reaction, okay? Also notice, looking at this plot, that the slope of this plot, the instantaneous slope at any point, would be what we call the instantaneous rate, right? The rate is changing as the reaction goes along. The rate starts off being fast because the concentration is highest at the beginning. The rate drops down, and in the case of the red curve, by the time I get over there to the far edge, the rate is essentially zero because I'm pretty much out of reactant, right? My curve has kind of flattened out, and so there's really no longer much reaction happening there, okay? So that just gives us a little bit of a look about how those two things would compare. I want to do an example looking at a problem that is the sort of thing we can solve with this. Okay, so here is a set of data for this reaction, which is the decomposition of N2O5. If you read in chapter 11, you'll notice a lot of the examples involve compounds of nitrogen and oxygen. That's actually because a lot of rate constants have been studied for a lot of different species involving those two elements, mainly because those are the two dominant elements in the atmosphere. So atmospheric chemistry involves a lot of different reactions between nitrogen and oxygen containing species. And so those have been studied a lot. It's just easy to get data for them. Notice a couple of things. Notice it says the data are at a particular temperature, 338 Kelvin in this case. That number, that 338 Kelvin, is not going to show up anywhere in anything we're going to do. The temperature usually is specified in a kinetics problem because the rate constant, remember, would change if we change the temperature, right? So the rate at which this reaction is going would speed up if I made the temperature higher, or it would slow down if I made the temperature lower. What have I got for a data set? I've got times, and I've got the concentration of N2O5, the reactant, okay? So I've got a data set that's concentration versus time. I can find the rate law from this, right? This is a different path than the one we did in the previous video, right? This is not the method of initial rates, because in that data set, we have concentrations and we have rates. Now we have times and concentrations, okay? So this is where I'm going to find the rate law graphically by comparing those data to my three models for the 0, first, second order reaction. Find the value of the rate constant. That's just going to come from the slope of whichever one of my test graphs gives me a line. Then we'll revisit that last question, which says, when, at what time will the N2O5 concentration have dropped to 1/2 of its original value? 1/2 would be when it's at 0.05, I guess, since we started at 0.1. So we can tell it's going to be somewhere in here, right, between 100 and 300. Looks like it'll be closer to 100, but we'll get a way to get an exact answer to that question by the end of working the example. So if I wanted to answer this question, the first one, find the rate law, basically find the order of reaction, what I'm going to do is I'm going to plot the data, and I'm going to plot them as concentration versus time. I'm going to plot them as log of concentration versus time, and I'm going to plot them as 1 over concentration versus time. These are my test graphs for 0 order, first order, second order, respectively. And then I'm going to look at those graphs and I'm going to see, is one of them a line? So I happen to have made those graphs. I did them in Excel and slapped them in here. So let's take a look. This is my, my 0 order plot, the concentration of N2O5 versus time. I didn't put any units on the graph, which is a little bit weird, but if you look at that graph, you can see that it's pretty obviously not a line. I did put in there the fit function, right? That's the trend line function in Excel. This number, if you're not familiar with this R² correlation coefficient, that thing would equal 1 if my data points all sat on the line. That's not a great looking fit. If you look at the data, you can see the points on the ends are systemically above the line. The points in the middle are below it. So my data is actually curving, right? It's clearly concave upward. And so it's not a line, so it's not 0 order. So we can leave that graph behind. This is the first order graph, log of concentration versus time, and that looks a whole lot better, right? Where my data points all seem to sit on the line. My correlation coefficient tells me it's very, very close to 1. So it looks like we have a first order reaction. I did go ahead and make the second order plot just for completeness, so let's take a look at that real fast. The second order plot, again, is a much worse fit. Right. Again, I have data that look like they're concave upward because the points on the ends of towards the ends of the line are above the fit, and the points in the middle are below it. If you just look at those points, you would not immediately say, oh, they're on a line, right? So this says that I have a first order reaction. Okay, so that says my rate is equal to a rate constant K times the concentration of N2O5, because that's my reactant. Okay. then I also get the rate constant from here, right? Because the slope of my graph is minus the rate constant. The slope of my graph is that number there, right? So the slope equals minus k. So that says k is equal to, the slope is negative, so the rate constant is positive, 0.0048. And that's going to have units of 1 over time. My times here were in seconds. So I do that. If you're not sure about the units for that, you can either remember that this thing has no units, so I get 1 over time for the slope, or again, you can look at the rate law itself and say, this is molarity per time, this is molarity, so that has to be 1 over time, okay? So that gives me a value for the rate constant, which means I could write my rate law now by taking this value and inserting it there for k, all right? So that answers the first two parts of my question. Let's skip past that graph again. Ooh, I'm sorry, I didn't know that was going to happen. So let's just put them all in there. Okay. Sorry about that. The question was that when would the N2O5 concentration be equal to 1/2 of its value? I could use the graph, right? And I could do an eyeball thing by finding where 0.05 is and dropping a line down and finding the time there. I can also just do this analytically using equations. So let's do it that way. My integrated rate law for the first order reaction looks like that. That really is the equation for the graph that was the straight line, right? My plot of the log of N2O5 concentration versus time. This is the equation for that. If I rearrange that equation to solve for t, I would get the expression on the bottom, right? That says I get 1 over k times the natural log of that ratio of the two concentrations, all right? I want to take that equation, which is put back here, right? Now, I want to put, I want the time where N2O5 of t is equal to 1/2 the original concentration. And this time, this actually gets a special name. It's called the half-life. So I'll put a T1/2 on there for that thing, right? But if I take this, if this says I want the number on the bottom to be 1/2 of the number on the top of this fraction, okay? So that makes the fraction that's in my logarithm become equal to 2, right? That ratio, the initial concentration is twice as big as the one when half of it is left. So that says I get this, which in turn says I get log of 2 over k, which is that number there, that 0.693 that I made the rate constant before. That's the natural log of 2. That's why I picked it for that. If I put into that equation my rate constant that we found, this 0.0048 seconds, and if I wanted to, I could have gotten more digits out of Excel for that. I get a time of 144 seconds to use up half of the original material, okay? Remember at the beginning, I said it was going to be between 100 and 300 and closer to 100. So we do sort of hit the right spot there. That suggests we've done things right, okay? This is what's called the half-life of the reaction. For a first order reaction, but only for a first order reaction, the half-life is independent of how much stuff you start with, okay? No matter what the initial concentration was at this temperature, after 144 seconds, half of it would have reacted and half of it would still be there. There are two places, two fields in which half-lives are commonly used. One is to describe radioactivity, because radioactive decay is always a first order process, right? So the half-life of a radioactive decay process is the amount of time it takes for half of the original sample to decay. The other place, somewhat oddly, where people talk about half-lives is actually in the pharmaceutical business, where people talk about the half-life of the active ingredient in a medication in your body, right? Where that's based on both if there's a decomposition of that ingredient, but also on just if your body is excreting it. And so people that figure out how often you have to take how much medicine actually use a half-life idea for that to make sure that you maintain a high enough level to be getting the benefits from that in the gaps between doses. So those are the two places where people use this the most frequently. I put this graph back here to make one last point about half-life, okay? So the red curve is the first order reaction, and because I picked that 0.693 rate constant here, that means for this one, the half-life becomes 1, right? Because T1/2 is 0.693 over K, it says there. And you can see that, right? If I go to the 1 second data point here, My Y value is pretty much right at 0.5. I go to the 2-second data point, and I'm at about 0.25, and so on, right? Notice when I get out here, I ran the graph out to 10 seconds, which is 10 half-lives. 10 half-lives is what people often use as a rule of thumb for how long it takes for the entire sample to be reacted. Obviously, this thing really is an asymptote, so you never, strictly speaking, get to zero, right? But people that do things like, I don't know, storing radioactive waste will say after 10 half-lives, your waste is getting pretty safe because then your concentration has been reduced by a factor of 2 to the 10th power. That's a pretty big number. Look at the half-life for the second order reaction, okay? After 1 second, I'm here. So I'm now coming out. My concentration is a little bit under 0.6, let's say, okay? I'm kind of bad at drawing these lines. But then at 2 seconds, I'm nowhere near half that, right? If I wanted to go, if I call that 0.6 for the sake of argument, then I got to be somewhere near 0.3. So my second half-life doesn't come until somewhere like that. Okay, so it's taken much longer to use up half starting with a lower amount than it did before. If I wanted to trace out the third half-life, it's going to be even longer, right? So the half-life for the second order reaction gets longer and longer and longer as the reaction goes along. That means the half-life is not a very useful idea for that. For a first order reaction, knowing the half-life gives you the same amount of information, the same amount of knowledge as knowing the rate constant. For a second order reaction, it really doesn't. And so for second order reactions or anything other than first order reactions, really, we by and large don't ever really talk about half-lives.